Thank you very much, sir, for giving me an opportunity to interact with the young minds and young peoples associated with the academics. I hope many of you are faculties from the different institutes as well as the students from this institute, right? So I try to justify the theme of this program, that is mostly related with the energy storage systems, and I will try to share my experience or my work during the last 10 to 15 years in this field. So as sir told that we are associated together since from our PhD, and I learned so many things from him. I started actually my PhD work under the indirect supervision of Professor Singh in IIT Delhi. He started me how to develop the simulation models and how to read the research papers. So I started like this. So today we are going to explore some of the studies which are related with the application of energy storage systems, either with the solar energy systems or wind energy system. Sometimes we have used this energy storage systems for hybrid applications. Means we have clubbed together the solar energy and wind energy. And in both cases, either it is connected with the grid supply system or it is with the state-owned system. So, as we all know that power system is now going to be in a transformation from the conventional systems to the modern power systems, where we are going to club the different kinds of ancillaries with our power systems. While we talk about the older periods, we have a one-way communications, we generate the power and we utilize this power at the input. But now the things are changing. The generation pattern is also changing, as well as the generation pattern is changing, the system demands, the load pattern will also change. So if we look at the power systems, at one end we have a mass scale power generations. Still today we have a mass scale power generations from the different conventional sources, and most of the power still we are receiving from fossil based systems. Right. Apart from that, the power system is coming with, if you look at the structures in between this center point, we are focusing that microgrid, and this microgrid is at the center, and then it is associated with the different utilities like your electric vehicles are there, then your different loads like smart loads are coming in pictures. And apart from that, energy storage system is also playing a big role in the control of your overall power system. Right? So, if you look at storage is concerned, at least 13 or 14 application of this energy storage systems are helping us. There are three big segments. We can classify the application of this energy storage systems in three big segments, where we have the different application of this energy storage system for this power systems. In due course of this presentation, we will discuss some of the points one by one. It plays a big role in the operation of the power system, either as an independent system operator or RTO, which we call the operator. Now the terminology is going to change. Now we are talking about the operators for our power systems. Apart from that, we have a different consumer services where the energy storage is playing a big role, and then utility services. Utility services means mass scale. We are talking about the application of the storage systems, in the field. Then just an overview about microgrid. What is microgrid and what we are expecting from this microgrid. So I hope most of you, because you already one week online course, and then this is the second last day of completion of your course, so you know about the microgrid. What is microgrid? Okay. So microgrid is basically two modes of operation. Either you are talking about normal mode of operation, or you are talking about isolated mode of operations. Normal mode of operation means your distributed generations. What are the distributed generations? Now, earlier time we have a conventional generation, so these generations are located far away from the user point. But now we are talking about the distributed generations which are close to you. Okay, where you are utilizing your power, your generation systems are also close to you. Maybe installed at the rooftop of this building, okay, in the form of solar energy, or maybe in the form of wind energy, which are close to your premises or buildings. Okay, so such kind of systems are coming. That's why we have a distributed. So the grid structure is there, then some metering application is shown here. So these are the distributed generations: solar, wind, biomass. Okay, and you have a user, maybe industry, maybe a residential building, maybe a commercial building. So when you are connected with the grid, the flow of power may be bidirectional. Sometimes the power may flow in this direction, and sometimes it will flow in this direction. It depends on what is our need and what is the local generation available to us. Okay. When generation is more, we'll feed the power to grid, and when generation will be less, we'll receive the power from the grid. Other important aspect of this microgrid is isolated mode of operation. In isolated mode of operation, you are completely isolated from your grid supply, and you have to manage your power locally with the available power. So if you have a less generation and the demand is more, then you have to think how you meet the demand or how you sacrifice with your demand. And when the demand generation is more and demand is less, then you have to think about how you are going for the surplus power. Right? Apart from that, mismatching of the power, you have to also think about the control of the parameters. What are the parameters which you are interested in controlling? Your loads are designed for the particular specifications. So you have to bond with these specifications. If you are talking that you can feed a voltage of 230 volt to your ceiling fan, then you should be bound for it. So then the issue of control will come in picture in isolated mode, which are little bit bigger or higher than while you are connected with the grid. Because when you are connected with the infinite grid, you have a lot of flexibility. Because the grid we are calling infinite grid, it acts as a infinite source or sink. As much as power you are producing or as much as power you expect, that can be supplied through this grid. So when we are talking about microgrids, then the role of energy storage systems are coming in a very big way. Way away from today, maybe 20 years, 30 years back, when this concept was not flourished too much. Okay, there are numbers of studies which has shown the relevance of this energy storage systems. Renowned agency of US, in one study they have shown that energy storage systems are going to be very vital in the coming future. In 2009, they have shown the benefits of energy storage systems. However, still today we are sacrificing with the efficiency of this energy storage systems. But fortunately, the energy storage systems are the one hope for us, which can be helpful in maintaining the mismatch between the generation and the utilization. So these are some of the studies which advocate for the different form of energy storage systems. Now when you are talking about energy storage systems, this energy storage system may be short-term energy storage system, moderate-term energy storage system, or long-term energy storage system. Each kind of energy storage system has its significance when we talk about the stability of your grids. Now come to the technologies available for energy storage systems. Okay. So we have classified in 3 broad categories. This is storage technologies, and based on this we have the different options. So here in this table, some of these technologies are listed. Start from your capture, which further enhances the super capture. Okay. Then you have a super magnetic energy storage systems. Then you have a flywheel which can also act as an energy storage system. All these are categorized as a short-term energy storage system because they can store not a very big amount of energy. Okay. They can store the energy, small amount of energy which can be delivered to the grid in the due course of time. After this, you have certain kind of battery energy storage technologies. Okay. So first one we started with lithium ion, which is now we are very much hopeful from this technology, lithium ion, and further research is going on. What is the expectation from the energy storage technology? क्या लगता है क्या चाहिए हमको, क्या इम्प्रूवमेंट चाहिए? अभी जो टेक्नोलॉजी अवेलेबल है, कैन वी हैव सम एप्लीकेशंस ऑफ एनर्जी स्टोरेज? कहाँ का यूज करते हैं इन आवर डेली लाइफ? हाँ, is it available with your mobile? Okay. What other applications? Vehicles, very good. Or is it available with your houses? Inverters. Okay. So now we are going to know that at many places we are, even if you talk about the LED lights, now these LED lights are also coming with certain kind of energy storage. When there is a failure of power, you have a backup of power for 2-3 hours. So you can have the illumination when your supply fails. So storage is coming in a very big way, and it is going to improve the quality of our life. Right? So lithium ion, we are mostly focusing on lithium ion. What is the reason behind this? Lithium ion. क्या कारण है जो लिथियम आयन पे अभी फोकस हो रहा है? Why not? Why you are moving away from lead acid batteries? If you compare these two technologies, what difference we are expecting? Energy density. This is one of the important factors. What others? Temperature, operating temperature. Okay. So we are expecting that the density will go on increasing. What benefit we will get if the density will increase? साइज कम होगा, और साइज कम होगा तो क्या बेनिफिट मिलेगा? साइज कम होगा तो कॉम्पैक्ट होगा. टेक एन एग्जांपल ऑफ इलेक्ट्रिक व्हीकल. इफ दिस बैटरी इज गोइंग टू बी कॉम्पैक्ट, ओके, व्हाट बेनिफिट यू विल गेट? For the similar frame size, what benefit you will get? You will have more mileage, okay? Efficiency will increase, okay? And more space is available for your comfort, right? So that's why our present focus is on lithium ion. But one of the big challenge with lithium ion is its cost, okay? Its temperature variation, properties variation with the temperature. Okay. So now research is going on, chemical engineers are working on it, okay, to provide us a much better technology. But presently we are focusing on lithium ion and we are moving on away from the other technologies. But still for large storage and for stainless steel applications, we are also using nickel cadmium, vanadium redox, okay. This form of energy is also utilized at stainless steel applications. Apart from that, if you talk about the large storage, large energy storage, okay. So some other options are also available apart from your battery storage systems. These are pumped storage, heat pumps, and another hydrogen. Okay. These are coming also in a big way for mass scale conversion or mass scale applications. So these are some of the features and properties of this energy storage systems. Now come with the flywheel. So we makes near about 2005-2006. One of the professors from McGill University has given this concept to use the flywheels. Okay. You know what are the problems when we work with the wind energy conversion systems or solar energy conversion systems? Why these systems are different than your conventional power systems, conventional sources of power like hydro, thermal, nuclear. What are the changes? Reliability. Okay. Agree? Partially. What others? Variable output powers. Okay. Their power output is not constant. It depends on what is the flow, what is the radiation. Sometimes you will have a sufficient radiation, sometimes you have a partial radiation, sometimes you have a shading condition, sometimes wind flow at rated condition, sometimes wind is excessive wind, okay. Sometimes you have a very low wind. Apart from that, if we talk about wind energy conversion systems, and if you look at the structure of wind turbine, when wind turbine rotates and even the wind flow is constant, still you will get some fluctuations in the output power of the wind turbine. This fluctuation will come because of the structure of your wind turbine. And these fluctuations are repeated. Okay. They are coming to, if your system is connected with the grid supply, then these fluctuations are continuously introducing to your network and it will create a big cause of voltage peak. So in this work, they try to minimize this problem. Okay, so what is done in this case? This is your wind turbine connect with a generator, it's a synchronous machine generator. Then first converter is there, another converter is there. These are the part of this wind energy conversion system. Apart from that, they have used one more converter, and with this one more converter, they are running an induction generator, induction drive. It is basically an induction drive, which is connected with a flywheel. It is connected to the flywheel, right? Now the first question is there, why these two converters are required here? What is the role of these two converters? Converter number 1, converter number 3, and then converter 2 is there. So these converter 1 and converter 3 are the conventional part of your wind energy conversion system. What is the use of converter 1? Basically, provide you the flexibility to operate this wind turbine at an optimum speed. How it will provide, how it will facilitate to operate at the optimum speed? It will facilitate by allowing this machine to operate at a variable speed. If it is a synchronous machine and if it is directly connected with the grid, what is its requirement? It should operate at constant speed. It should operate at synchronous speed. Okay, if it is a 4-pole machine, then and your supply frequency is 50 Hz, so this machine is supposed to operate close to 1500 RPM. Okay. But when you run at 1500 RPM, allow this machine to run at 1500 RPM, then the wind turbine is also bound to operate at a constant speed because it is directly coupled either through the gearbox or it's a direct coupling. Okay. The machine is directly connected. So wind turbine is also bound to operate at a constant speed. And if you allow the wind turbine to operate at a constant speed, you may not be able to extract the power from the wind turbine. Okay. So for that purpose, it is essential that you operate this machine. You allow this machine to operate at a variable speed. But when this machine operates at a variable speed, the output frequency of the machine is going to change. So you need a certain kind of system which allow you the operation of the machine at a variable speed so that you have a maximum power extraction from the wind turbine. Okay, and you convert this power in the form of DC with the help of certain converters. Okay, so what is the role of this converter? It allows variable speed operation and convert this variable frequency supply into a DC supply. So this is your DC link. Okay, then from this DC link you need, because now you have to feed this power to the grid, and grid has a constant voltage, constant frequency system. So this converter allows the operation to transfer this power from this end DC link to this grid. Right? So that is possible through the rectification. Okay, you convert the available available DC into AC. So we call the operation is inversion, not rectification. Okay, DC to AC. Although we have certain means and certain provisions to convert this power from DC to AC. Okay, so if by the geometry of this wind turbine, even the wind speed is constant, if this geometry, the power which is at this point is fluctuating, the fluctuating power is transferred to the DC link, and the same power, because you don't have the energy storage here, we are using a capacitor. Capacitor is it is just to maintain the DC link voltage. Okay. So what you will do, you will have the reflection of this fluctuating power at the grid side, and when such number of wind turbines are connected with your grid, then the effect will be cumulative, and you will have a voltage flicker in your grid supply, voltage flicker to your customers. Okay. So what you can do in this work, what was suggested, what you will do, you will absorb the value which is above your average value through this flywheel system. So when there is a excess power, momentary excess power is coming, this excess power is going to your flywheel, okay, through this induction motor drive. So energy will be stored, the speed will increase, and flywheel is stored the energy in the form of kinetic energy. And when there is a fall in the power because of 3p oscillations of the wind turbine, you will supply the energy here. So here, this capacitor at the intersection point, you will have a straight kind of power supply. When there is a deficient power from this end, you will feed the power through this, and when there is excess power, you will absorb this power. So at constant wind speed, this converter is going to absorb a constant power. Right? So basically here you are going to store intermediate energy, small energy during this time. Another one which uses a super capacitor. So the same system, and only the machine is changed. Here you have a DFI, W-fed induction generator, you have a DC link, your converters are coming at the rotor circuit, not at the stator circuit. Okay, and in the DC link again you are using, now in the previous case you are converting the electrical energy into the kinetic energy, and from kinetic energy again you are converting into electrical energy. So overall charging and discharging, like your battery, the efficiency was not very good. But in place of that, if you use a converter, which is a bidirectional converter, because it's a DC, so you need a DC to DC converter, and at the output terminal of this DC to DC converter, you have some short-term energy storage option. You can store the energy, you supply the energy. You store the energy, you supply the energy with the help of. So it's a kind of buck boost operation. When you are receiving the energy from the main DC link, it's a buck operation, and when you are supplying the energy back to the main DC link, it's a boosting operation. Rest of the thing is same in this sense. So this is another example, just shown that this system can also be used for fault right through enhancing the fault right through capability of your wind turbine. I hope you have gone somewhere through, because this system is also expected according to certain IEEE standard guidelines that when this kind of renewable energy system should be connected with the grid, and up to what point they should be in the system before disconnecting. Because if you are connecting the system and disconnecting, there are a lot of disturbances in your system if you are going to remove the systems from your main grid. You will offer a lot of challenges. So basically, in this case, what you are doing, we are trying to increase the fault right through capacity, fault right through enhancement. The same application, same storage systems are used for the fault time right through enhancement. So, what is basically fault right? What condition is going to take place in the fault right? Fault right is observed or noticed with the help of what is the per unit voltage at the grid side. If there is a fall in the per unit voltage at the grid side, then that place will be considered to be a fault right case. So, in the first case, your power is flowing like stator power is going to grid because the voltage is healthy. It's a healthy condition. Okay, and you are receiving the power from the rotor. Okay, this can act to store the energy depending upon how much power is generating. If you want to maintain a constant power, so this energy storage system will store the energy. If you want to reduce the power, then it will supply the energy. Under the fault conditions, the voltage at the grid will reduce, and that time it is required to provide a support of large reactive power to your grid, because voltage is going to collapse. To maintain the voltage, you have to increase the reactive power injection to the grid. So basically, during this time period, what you are doing, your energy storage system is doing, it is trying to store the energy which is generated through your wind plant, okay, during that time period, and this stator and the rotor converter is utilized to inject more amount of reactive power to your grid, so that your system will remain sustained in the grid supply. This is a case of two-level energy storage systems, short-term and intermediate. So basically, it is divided in two parts, and some AN-based approach is used, okay, through which you can have the energy storage. So for short time, meeting the short time energy storage demand, you will use one converter, and for medium term energy storage demand, you have a different kind of energy storage system. Then you have a hybrid kind of energy storage system. Okay. So here you can look, conventional capacitors are there, ultra capacitor steel is also there, which has a little bit higher capacity to energy for energy storage, and then you have an energy storage system like lithium ion or lead acid kind of energy storage system are also there. This is the same case which we have discussed earlier for mitigating the voltage flicker because of wind power. Now, when we talk about the application of this energy storage systems, so now energy storage systems are with you. You have the specification of energy storage systems, and we also realize that this is the demand of the present structure of the grid that you have to use the energy storage system, particularly with renewable energy sources. So what are the possible options which we can use to utilize this energy storage systems for mitigating these problems? Okay. So basically, in our previous work, we have proposed some 2-3 schemes which are possible to be interfaced for this energy storage systems. What are these schemes? Initially we thought that we use battery to charge when grid low demand is less. Okay. Then the wind generation. Okay. So what will be the indicators at the grid side when your load demand is going to less? आपका अगर ग्रिड सप्लाई पे आपके डिस्ट्रीब्यूशन लाइन पे वोल्टेज का स्टेटस में कुछ चेंज होगा अगर लोड डिमांड कम होगी तो. टेक एन एग्जांपल ऑफ योर वोल्टेज इंक्रीजेस, okay, and when load demand increases, voltage falls. So this may be taken as a proximity indicators to design this control scheme. Okay. So battery charges when load demand is less than the wind generation and discharges when load demand is greater than wind generation. Okay. That's simple study. क्या एडवांटेज मिलेंगे इसके हमको? मिनिमाइजिंग एक्टिव एंड रिएक्टिव पावर लाइन लॉसेस. इफ यू टॉक अबाउट अ डिस्ट्रीब्यूशन लाइन, वी आर टॉकिंग अबाउट अ डिस्ट्रीब्यूटेड जनरेशन. ओके. सो फॉर द डिस्ट्रीब्यूटेड जनरेशन, if you are using the battery energy storage system with your wind plant, like you have located a 100 kilowatt wind plant at certain points of your distribution line, and you want to use the energy storage system. So what should be the strategy that is presented here? तो उसके एडवांटेज आपको क्या मिलेंगे? एक्टिव और रिएक्टिव पावर आपकी लाइन लॉसेस के कम होंगे. Then you will be able to reduce the stochastic effect of wind on distribution network. Availability of large power under wind disturbances to support the grid. जैसा हमने पिछले केस में देखा, फॉल्ट राइट के केस में अगर एनर्जी स्टोरेज हम यूज करते हैं और अगर आपके एनर्जी स्टोरेज का साइज सफिशिएंट है, so you can use the facility available with your DFIG or your back-to-back connected converter to provide the reactive power support to your grid, and you can store the energy which is generated through your wind plant during that time. Then it may be helpful for maintenance of wind plant in presence of storage systems. Merging stochastic behavior of wind and consumer loads, that is also possible. When consumer needs more power, you can supply because the storage is there. When consumer demand is less, you can store into your storage system. This is one strategy. Another strategy which is possible is that you dispatch the average wind power to the grid based on hourly, daily or weekly forecast. I hope you know that we can forecast. Okay, there are certain algorithms which are available through which we can forecast what will be the wind power generation tomorrow or what will be the wind power generation next week. That can be forecasted. Some algorithms are already reported in the literature, and these algorithms are also used for the industrial setup. So we will dispatch the average wind power for your wind power stations, and battery charges when instantaneous wind power is more than the average forecasted power and discharges during the instantaneous wind power. इसका मतलब what we are going to propose? We are going to propose in second control strategy that we will find out what is the, जैसे we are talking about 1 hour. So in 1 hour, if we have the forecast of wind, okay, even the wind speed is going to vary. Maybe some moment of time your wind speed is 6 meter, another moment of time wind speed is 10 meter, another moment of time 12 meter. We'll take what should be the probable power generation during 1 hour. We'll take the average value of this power generation. Okay? Because grid will be very much happy if you ensure that during this hour you will feed this much power. Okay? And we will dispatch this wind power based on this forecast to the grid, and we will manage the control of the charging station in such a way, battery storage systems in such a way that will absorb the power when the instantaneous power is greater than your average power, and we will release the power when instantaneous power is less than the forecasted power. Okay. This may be one of the strategies. So how it will be helpful? It will improve the stability of your network, because you are ensured that during this particular hour you are committing that this much amount of power you can dispatch. Phenomena of voltage flickers can be minimized, because now you are taking out all the fluctuations which are because of your wind power. Grid is not going to bother that what is this voltage flickers are there. Reduce intermittent power injection into the grid. Storage unit size and its capacity can be minimized. Depending upon आपका कितनी देर का commitment है उसके corresponding you can have the specification of your storage system, right? Another study which may be possible apart from the already established study. Dispatch storage for curtailment of low frequency variation in wind power due to wind shear and tower schedule. Okay. Now in this particular case, we are simply talking about the fluctuation in the grid injected power because of wind turbine, which considering the effect of wind shear and tower schedule. Means continuously if your wind speed is constant, then also you are getting a fluctuated wind power into the grid system. So now in this case we are simply talking about this. The sole objective is to reduce the size of the storage system. Reduce the size of the storage system. So इसका एडवांटेज आपको क्या मिलेगा? स्टेबिलिटी इंप्रूव होगी, वोल्टेज फ्लिकर्स का इफेक्ट आपको ग्रिड पे नहीं दिखेगा, शॉर्ट टर्म एनर्जी स्टोरेज इज सफिशिएंट और अ लार्ज साइज कैपेसिटर एट द डीसी बस इज सफिशिएंट. That is possible. Try to simulate this strategies. Okay. But when you are talking to simulate this strategies for the real-time systems, okay, you need either you have to use a costly softwares, like this kind of facility is possible with your Homer software, P-Skate, P-Tape. Such studies are possible there. Okay. But when you are talking to explore these things with the openware softwares, okay, or your MATLAB, okay, then you have a little bit issues. The issues are that you don't have the complex size of network in your model. You have to model this, and when you are going to model this, the simulation speed is going to reduce us. So initially what we do, the first challenge is that you should have the realistic wind model. Okay, because while you are simulating the things, okay, you cannot have your wind turbine models are not good enough, which will consider all these effects. In MATLAB, those are using the MATLAB, they can see that in MATLAB you have the wind turbine model. But wind turbine model, the inputs are you have to apply the wind speed. Okay. Then you have to say what is your blade angle or pitch angle, and then what feedback signal is coming to your turbine. This much facility is available. But when you try to simulate this effects, this facility is not available to your wind turbine. So what we have done, okay, we have developed all these effects in the wind speed model itself. So if your wind has all these effects, then definitely it is going to reflect on your turbine output. So we have considered these effects, which are the realistic effect in real time. Okay, equivalent high wind speed, equivalent wind shear component, equivalent tower shadow component, second and third component produces deterministic aerodynamic blade passing phenomena, and equivalent wind speed is a function of time and blade position angle, which is defined with this expression. So this is your equivalent wind speed. Then it considers the shear effect and it considers the tower shadow. Now you can have to find out all this. You have to mathematically model all these effects. So how you can mathematically model? That is presented here. So this is your average wind speed. Then this is the fluctuating wind speed, which should be considered in the effect. So for that, we obtain that if you use a Kalman shaping filter, which will exactly going to reflect the stochastic component of the wind speed. So this camel shaping factor is introduced in the model, and its parameters are considered in this case. So where L is the turbulence length, what is the turbulence length, and this Kf is the gain. Then this is deterministic components, which consider the tower shadow effect and wind shear influence. So these expressions are derived to consider all this. Basically, these are the components of your wind turbine. So what is wind height, what is blade height, what is blade length, what is the space from your ground to center of your vehicle. Okay, all these parameters are considered. So here R represents the blade radius, H is the hub height, A is the tower radius, X is the blade origin from tower middle line, and A is the wind shear component. For the different types of turbine, this wind shear component is going to be different. Like you have a vertical axis turbine, you have a horizontal axis turbine, you have a helix turbine. So all these components are going to vary for the different ratings of your turbine. Okay, so now the first thing is that the model which is developed is okay or not. You have to verify. So how we verify it? Okay, then we have taken an input to your wind turbine with the help of this expression, then the wind speed looks like this. Okay. Now it is not a blade. All the effects are coming in picture. Okay. So these are close to the realistic effect. Okay. Then we have observed these effects, equivalent effect in the speed of the wind turbine. Okay. That model is developed. And we observe that if suppose 1 megawatt turbine you develop and the input to 1 megawatt turbine is this much wind speed, then what are the fluctuation in the actual speed of your turbine? That is observed here. And then later on, this is basically the power produced by your wind turbine. Okay. यहाँ पे wind speed constant है, maybe around let's say mean speed is 10 meter per second. Okay. So if you give a 10 meter input signal to your wind turbine, you get a constant output. So Pg will remain constant, but in reality this is not the case. Okay. So your power output is now, when you model the wind speed like this, your power output is coming like this. Now you have to again verify that the components, harmonic components or power density which is present in your wind model is also present in your output power. So for that we have to see the power density, power spectrum density of wind speed. So when you look at the power density spectrum, this is the power density spectrum of your wind speed. It looks like, and this is the density, distribution of the density. And the similar density you are noticing on the generated power. So it means it is verified that the model which you have developed and the effects are coming into the generated power. Now another case is that now you have to develop the model. Okay. The model which will help you to study the effects of this fluctuating wind power, which considers all effects like wind shear, tower shadow, turbulence and speed. All these effects should come to your distribution grid. So for that, what we have done, we have taken an IEEE 13 bus system. Okay. This is basically IEEE 13 bus system. And with this IEEE 13 bus system, we have identified the location at which node we can connect at least 1 megawatt power plant. Okay. So we have connected a 1 megawatt wind power plants. And because now in MATLAB you know that the study can be different types, like you have a discrete simulation, like you have a continuous simulation, or you have a phasor simulation. While you try to run this model on discrete simulation, then it takes a very long time. Okay? And to observe that आपने जो model develop किया विंड टर्बाइन का, उसके इफेक्ट जो रियल ग्रिड में आते हैं, जो कि वो वोल्टेज पिकर वाले जो रिएक्शंस आते हैं, वो रिएक्शंस आपके मॉडल में आने के लिए सबसे पहले तो आपको ये तैयार करना है आपको। तो जब आप डिस्क्रीट सिमुलेशन करोगे तो बिकॉज योर सिमुलेशन इज रनिंग एट अ वेरी डिस्क्रीट टाइम एंड इट्स कॉम्प्लेक्स मॉडल, 13 बस का मॉडल है, वैरायटी ऑफ लोड्स आर देयर, मेगावाट लोड आर देयर, ओके, डिफरेंट काइंड्स ऑफ लोड्स आर देयर, सिंगल फेज लोड, 3 फेज लोड्स, बैलेंस लोड, अनबैलेंस लोड, ये सब टाइप के लोड्स हैं। और उसके साथ में आप 1 मेगावाट का पावर प्लांट चलाने की कोशिश करोगे तो इनिशियली वी वेट फॉर 1 वीक, दिस इज ऑन एंड वी आर वेटिंग फॉर द रिजल्ट्स। Okay, at least you have to run your model for near about 1400 minutes. Then you come to know that leakers are present in your developed power or not. कम से कम हमको 1400 मिनट चलाना पड़ेगा अपने मॉडल को. So we waited for 1 week and we came to know that model, the simulation is progresses just for 2 minutes. Okay, so we stopped. And then we tried for the phasor simulation. Okay. So we developed this model for phasor simulation. Okay. And we could succeed to develop this model for phasor simulation with this control algorithms. Okay. And in this model we tried the third control scheme which was proposed just to curtail the voltage flickering. So what we have done, you consider an energy storage system at the DC link. It is directly interface. This is your PMSC based wind turbine. So wind turbine coupled with a very low speed PMSC, and then you have a machine side converter, you have a grid side converter, and then you are interfacing with the grid. And here you have a very small rating of the storage system. And then vector control is used for machine side converter control, and also the vector control is used for the grid side converter, and the reference power which is going to dispatch to the grid has been obtained through the average power produced from the machine side converter. And for that we tried for some 3-4 different cases. Suppose we take an average of 10 सेकंड, कि 10 सेकंड में यहाँ पे जो पावर प्रोड्यूस हो रही है उसका एवरेज ली, और ग्रिड साइड कन्वर्टर को इंस्ट्रक्ट किया कि उस एवरेज पावर के करस्पॉन्डिंग ग्रिड को पावर इंजेक्ट, ठीक है। फिर हमने क्या किया, दूसरी स्टडी की कि इसको 10 सेकंड के बजाय इसको 1 मिनट का एवरेज पावर लिया, और फिर वो 1 मिनट में जो एवरेज पावर आई उसको हमने ग्रिड से इंजेक्ट किया। We'll try to investigate that how much size of energy storage required if you change this averaging thing. So this is the mathematics I have designed. I am skipping just. You may have in your slides, you can refer it. Okay. Now we come to the observations. Results. In first observation, जो एवरेजिंग कर रहे हैं पावर की, जिससे आप ग्रिड कन्वर्टर को इंस्ट्रक्ट कर रहे हो, that averaging is obtained for 1 second. Okay, initially we start with 1 second. So 1 second में just focus on this result. The first one is your wind speed. The second one is the speed of your PMSG rotor. Okay. The third one is the torque produced by electromagnetic torque produced by your generator. The fourth one is the DC link. The fifth one is the power injected to the grid. Okay, and this is the substation power, and this is the reactive power available at the substation. So here you notice with 1 second averaging, the power produced by the generator and the power injected into the grid, this is the power produced by generator, this is the power injected to the grid, has not a very significant differences. बहुत ज़्यादा difference नहीं आया है. Okay. Now come to the another case where the averaging is taken for 10 hertz, 0.1 second. Here if we notice So this is your power injected into the grid. Little bit it is thinner than this wind speed. Okay. जो इफेक्ट यहाँ थे वो इफेक्ट थोड़े से यहाँ पे reduce. Then we further increase 10 seconds. Okay. This is 10 second distance. So here you can notice reasonably these effects are going to be flattened in this case. But although some glitches are there, okay, these glitches are coming in. This is the power spectrum density. Power spectrum density for generated power and power going to the grid. Now you can notice the differences in this, the distribution of this power for the different frequency components. Okay, this is the generated power. It is little bit wider, but while the power which is fed to the grid is little bit thinner. Means it is more concentrating towards the fundamental value, while it is little bit distributed away from the fundamental value. Okay, zero means fundamental value. Okay, while you are moving away from zero means fluctuations are coming. So, in nutshell, the conclusion of this work is that we can optimize the size of the storage depending upon our applications. Okay. It is not a good idea to go for a very high size of the storage because we know that there are a lot of issues with the storage. If we are going to increase the storage, definitely all these parameters will come in picture, which we call the cost of your storage system, its maintenance of the storage systems, life of the storage systems, all this comes in picture when the size is going to increase. So overall power generation cost will increase if the storage size is going to increase. But so how can we minimize the generation effect? By optimizing the size of the generation, size of the storage and the quality of the supply. These are the further results if you go for 20 seconds and then other cases with the MANIT. So we explored another software which is freely available. Okay. That is OpenDSS. This software was developed by Professor Rosen Duggar from US, April. Okay, and the software is freely available to everyone. We can install this software and we can run this kind of simulation strategy on this software. What are the features? It is very flexible and a foundation for spatial distribution analysis. Distribution analysis we can easily do on this software. Fill gap left by other distribution system analysis tools. This do very well in traditional distribution system analysis, meeting the needs of their respective user bases. Integration of user interface. One of the beauty of this software is that you can interface with other software also. It's a freely available, but you can interface with MATLAB also. You can interface with your PCM also. You can interface with your Homer also. So other interface is also possible. So, because in MATLAB we all know that it's quite comfortable to develop the control scheme and algorithms. Okay. But the structure of whole distribution system is little bit complex when we go to develop. So what we can do, and the another beauty of this OpenDSS is that all the codes for different IEEE standard bus systems are there, like IEEE 13 bus, IEEE 30 bus. Okay, even a large network is also available there. That is IEEE 8500 node is also available. You can do here, power flow study is possible, harmonic analysis is possible, dynamic study is also possible. EMT analysis is not possible till today, but people are working to enhance this software for EMT analysis. Now, what are the options possible? Okay. We talk about 3 control schemes for energy storage system, but by default some control schemes are also available with OpenDSS. What are these control schemes? You can have the discharge in default mode, or you can have discharge energy storage discharge in follow-up mode, or you have a price mode, or you have an external. So these three are the default mode. External mode facilitates us to develop our own scheme, control scheme, and interface with it. What is price mode basically? You know that presently distribution system operators are going to be independent. Okay, ISOs are coming in market. Okay, so this ESOs and ISOs, according to the price, they offer the price mode. Okay, they offer price mode to your customers. Okay, so if suppose in some DSO this energy storage systems are connected, then the charging and discharging of this energy storage systems can be clubbed with the pricing. Means now they are offering that when they have a more demand of power. Okay, so during this time period, what is going to be happen? They will charge to the customers little higher, like in evening time when the load demand is high. So that time your DSO discourage you to increase your consumption. They encourage you to reduce the consumption during the peak time. Okay, according to the demand response strategy. So what can be done? If you are suppose you are a private player of energy storage system installation, so you can club your charging according to the price. जब power की price कम है उस समय आप energy storage में रिसीव कर लो एनर्जी, और जब प्राइसिंग जा रही है, जब बढ़ रही है, उस समय आप अलाउ करो अपने स्टोरेज को डिस्चार्ज करने. So that is basically this facility is available with this open DSS. So you can develop your model and according to the price mode you can dispatch or receive the energy. Okay, but here our objective is different. We want to validate our control scheme, so we use an external mode. Okay, so storage controller is used in external mode. So we developed control algorithm for dispatching the storage using its communication code interface. Okay, we tried this scheme with this IEEE 8500 node system. It's a very large network. Okay, and we tried with 2 megawatt wind power plants, okay, and 2 megawatt solar power plants. So with this complex system, we introduced 2 megawatt solar plants at these locations. So we installed, basically it's a structure. So we identified what are the feasible points where we can introduce wind power. ऐसा नहीं है कि आपने नोड पे कहीं भी कनेक्ट कर दिया. Okay, हमको आइडेंटिफाई करना पड़ेगा कि कहाँ गैप्स चाहिए जहाँ पे हम लगा सकते हैं. Okay, from couple of years this studies are already in practice to find out the optimum location where you can introduce your renewable energy. So that kind of study has been done and we identify the locations. So एक PV प्लांट यहाँ पे कनेक्ट किया 1 मेगावाट का, एक PV प्लांट इस लोकेशन पे कनेक्ट किया 1 मेगावाट का, एक विंड प्लांट 1 मेगावाट का यहाँ कनेक्ट किया, और एक विंड प्लांट we have connected. Oh sorry, this is 2 megawatt wind plant. These are the 1 megawatt PV plants. So 2 PV plants और एक 2 megawatt का wind plants. ये इस नेटवर्क में कनेक्ट. These are the specification of this network. इसमें 8541 nodes हैं, 4876 buses हैं, 6104 devices हैं. Okay. So these are the specifications. Then we have a substation transformer जिसका KV है 150 और उसका डिस्ट्रीब्यूशन वोल्टेज है 12.47 and this MVA is 27.5. There are voltage regulators, there are single phase 3 winding load transformers are also there at different locations. So this number is high, and these are the various lines, maybe single phase line, 3 phase line. Okay, these lines are there. So these are the specifications available in the literature. You can see it. और जब इस पे आप load flow solution अपना चलाते हो, okay, open DSS allow you to run the load flow solution. So when you run the load flow solutions, फॉर द बेस केस, जब आपका कोई विंड प्लांट नहीं है, कोई सोलर प्लांट नहीं है इसमें, जब आप स्टैटिक लोड फ्लो एनालिसिस जब इसमें करते हो, सो व्हाट यू विल ऑब्जर्व, द मैक्सिमम पर यूनिट वोल्टेज इज गोइंग टू बी 1.05, okay, and minimum per unit voltage at a particular bus is going to 0.92, okay, and total active power demand by the load is around 11.98 megawatt at the substation transformer, and reactive power demand is 1.38 MVA. Total active power losses are going to be around 1.21 megawatt, 10% of the total power consumption. Please notice it, okay. The power consumption is around, active losses are 10% and reactive losses are also high, it is 2.76 MVA. And this is the power density, loss density and voltage at various nodes. These are the power density, loss density and voltage at various nodes of this system, okay. जो लोकेशन जहाँ पे हमने इसको कनेक्ट किया है, वो लोकेशंस पे कुछ इस तरह से कनेक्ट किया। ये आपका विंड प्लांट है, किस पर्टिकुलर बस पे कनेक्ट किया है इसको, उसका नंबर है LN637554 एंड द स्टोरेज इज कनेक्टेड एट दिस सेम बस जहाँ पे विंड प्लांट। देन you have to also define the load profile, because your study will not be formed if you simply run with a constant load. So your, अगर हम अपनी load की profile को भी vary करें, okay, so the load profile is varying like this. This is the आपका wind speed का जो आपने मॉडल किया, okay, तो 1400 सेकंड के लिए आपका wind profile, 1400 मिनट्स के लिए आपका wind profile कुछ इस तरह से जाएगा, और ये आपका PV का जनरेशन का। These are the standard data for PV which are available at the different sites like EPRI and NERC, all these locations you will get the standard wind profiles. Are you able to follow what we are discussing up to certain extent? If any questions by that part, we can have an interaction and we will continue. अगर कोई questions है तो we can discuss right now. Okay. तो सबसे पहले क्या किया? बेस केस एनालिसिस। आपने विंड प्लांट कनेक्ट नहीं किया, ओके, आपने सोलर प्लांट कनेक्ट नहीं किया, और उन बसेस पे आपने स्टडी की, उन बसेस पे स्टडी की जिन बसेस पे आप ये विंड प्लांट और सोलर प्लांट कनेक्ट करने के लिए, राइट, जस्ट टू ऑब्जर्व द हेल्थ ऑफ योर सिस्टम, व्हाट इज द हेल्थ ऑफ द सिस्टम एट दैट पॉइंट, ओके. सो ऑब्वियसली वी हैव रन लोड केस एनालिसिस, लोड फ्लो एनालिसिस एंड वी ऑब्जर्व द डिफरेंट पॉइंट. तो ये उस बस का डेटा है जहाँ पे हम PV नंबर 1 कनेक्ट कर रहे हैं 1 मेगावाट. ये उस बस का है जहाँ पे PV नंबर 2 कनेक्ट करने वाले, अभी कनेक्ट नहीं किया, बेस केस में एनालिसिस कर रहे हैं. और ये एनालिसिस कैसे की? दिस रिजल्ट्स आर ऑब्टेन्ड एट मैटलिब, ओके. फॉर्म सर्वर्स, फॉर्म यूटिलिटी इसकी यूज की, इंटरफेस की, और ये रिजल्ट्स फ्रॉम के मैटलिब. ऑल्दो द प्रोग्राम, बेस केस प्रोग्राम इज ऑन OpenDSS, राइट. So these are the base case results. Will come with the case when we are going to introduce the renewable energy. OpenDSS, this IEEE 8500 bus model is there. You can control the operation of this model through your MATLAB or any other software, right? So that is controlled from, in this case. And also you can modify this model with the help of MATLAB. Suppose we are going to interface 1 megawatt power plant. So we are interfacing through MATLAB, not through OpenDSS. मतलब OpenDSS के प्रोग्राम में कोई चेंज नहीं किया, वो बेस केस का प्रोग्राम वैसे ही हमने वहाँ इंट्रोड्यूस कर दिया एक बस पे. So दिस इज द पावर जनरेशन प्रोफाइल, जैसा आपने विंड का प्रोफाइल दिया था उसके करस्पॉन्डिंग आपको पावर जनरेशन मिला, एंड दिस इज द रिएक्टिव पावर. ओके, रिएक्टिव पावर इंजेक्टेड बाय पीवी प्लांट एट दिस पर्टिकुलर बस. ओके, what is mentioned here, this 1 megawatt PV plant is controlled in volt watt. Okay. You know that when you start a converter of your PV plant which is interfacing the solar PV panel to your grid, that what should be the probable rating of this converter? Suppose I am going to connect a 1 megawatt power, तो कितनी रेटिंग होना चाहिए इन जनरल उस कन्वर्टर की? 1 मेगावाट का पावर प्लांट है तो कन्वर्टर की रेटिंग कितनी होना चाहिए?
1 megawatt plus safety rating.
Yes. Roughly you can say it should be 1 MV. If your converter is operating at 3D power factor, तो कम से कम 1 मेगावाट का प्लांट है तो 1 मेगावाट की पावर उसमें कैपेबिलिटी होना चाहिए कि 1 मेगावाट की पावर डिलीवर कर सके. Of course, there should be some safety also. Okay, so 10% or 15% that safety should also be come in picture. And the issue is that if you look at from this point to this point, that PV is not producing any power. Okay, it means PV plant is not producing any power because either you are in the night time or you are at the beginning of your day. So most of the time your wind power plant is ideal. Okay, it is not, this converter is not utilized for any purpose. So what you can do, you can take the capacity of this PV converter to either supply the reactive power or inject the reactive power to your grid during this time. Isn't it? जब हमारा पीवी का जनरेशन ही 0 है, कन्वर्टर की रेटिंग अगर 1 MVA की है और वो आइडियल पड़ा हुआ है और मोर देन 12 आवर्स, so why not to utilize this facility to either supply the reactive power or consume the reactive power. Why you want to supply the reactive power or consume the reactive power? What should be your objective? क्या हो सकता है objective हमारा? Why you want to consume or absorb the reactive power at a particular bus? What is the use of D-state pump? हम D-state pump क्यों use करते हैं? Yes, for voltage regulation. For voltage regulation or for maintaining the quality of supply at that. Okay, we use D-state pump. So the same system means that converter can be used to work as a D-state pump during the ideal period. Apart from that, if you look at the power profile, okay, you have a very less time when you have a full power generation. Otherwise also, like when you are starting from the morning, radiations are not to be at peak 1000 watt per meter square. The radiations are little bit growing, and near about 12 o'clock to 3 o'clock you have the maximum radiation if you have a clear sky condition. Okay. Otherwise the radiations are less than this. So why not to utilize the reserve facility of your converter for exchanging the reactive power, right? So this converter, which is interface your PV plant to the grid, is controlled in volt war. Volt war mode means I am interested to use, I can develop an algorithm that I will check what is the active power generation.
Break करना है? 5 मिनट का break करना है.
Okay, we have a break.
We have a break for 5 minutes to break after. After this FDP, YouTube पे हमें अपलोड करना है विद द सेम नेम जो एक्टिविटी करने हैं. तो आज ही नहीं, आप 2 साल बाद भी आपको लगता है कि वो सर ने कुछ बताया था हमें याद नहीं है, तो आप YouTube से डाउनलोड करो और सुन लो लेक्चर. ये बिल्कुल ओपन एक्सेस में रहेगा. तो ये सारे लेक्चर्स जो हुए हैं 14 लेक्चर्स वो सब YouTube पे डलेंगे. उसको थोड़ा सा हम लोग वो करेंगे क्योंकि इन बिटवीन वी आर हैविंग लॉट ऑफ डिस्कशन ब्रेक्स, तो उसको मॉडिफाई करके कॉम्पैक्ट करके, और ये सारे लेक्चर्स ऑल 14 लेक्चर्स जो हुए हैं दे ऑल विल बी अवेलेबल ऑन यूट्यूब। तो जो डिस्कशन अगर आप बाई चांस मिस भी कर रहे हो ना, वो डिस्कशन आपको दोबारा जब सुनोगे तो आपको याद आ जाएगा कि यस व्हाट वाज दैट डिस्कशन, ये पूरा रहेगा। तो इसकी ज़्यादा टेंशन नहीं करो आप कि लेक्चर मिलेगा नहीं मिलेगा, वो सब अवेलेबल रहेगा। ओके, सो वी कैन कंटिन्यू।
Okay, so we are discussing the first case. So in first case, this 1 megawatt wind plant is introduced in this network, and this is controlled in volt-var mode. Okay? So volt-var means the basic objective is that utilize the facility of your converter, which is used for PV plant for some other purpose, which helps to stabilize your grid, right? So either during the night time or when you have a less power generation to the wind flow, that facility is used to stabilize your grids supply. So this is the reactive power injected by the converter, which is with wind power plant number 1. Then we look at this point. If you look at SOC, this is 0, because right now we are not going to use energy storage system. Okay, this is the first case where we are going to, in the base case we don't have any renewable energy sources. Now we are introduce the renewable energy sources, but not with the storage. We want to observe that how the system is behaving when renewable energy sources are introduced in the grid, this grid. And now I am coming to this point. This is the bus voltages, phase A, phase B and phase C at the node where we have connected with power plant number 1. So you can notice these are close to 1 per unit. Still, when we have some glitches in the power generation, there are disturbances are coming at the same node. Right now we are controlling in volt-var mode. Similarly, we have the control in volt-watt mode. Okay, you are controlling the voltage at which your converter is connected, corresponding to watt injected into this network. And then one more mode is possible that we call dynamic mode. In dynamic mode, you will sense the rate of change of injection, and corresponding to that to inject the reactive. Okay, rate of change of injection of current into your network. Okay. So this 3-4 kinds of modes are available in the literature that can be used here. So here you can notice this is the reactive power injection by PV plant 2. But here, as compared to the previous case, here you will have a sufficient reactive power injection. But in this case, the reactive power injection is limited or in the reverse sign. Why? Because at that point, at that node, the reactive power injection is not required to stabilize the voltage. That's why your converter is not injecting any voltage, any reactive power to the grid. So you can notice here, because here without much injection you are close to the reference point 1 pu, voltage is at 1 pu. Then come to the wind power plant. So unlike your PV plant, the case here is not that your wind power plant will not produce any power round the clock. Okay, whether it is a daytime or night time, wind speed is going to change, but the power generation is not going to completely vanish. So here we have just used the wind power plant to supply the active power at that moment. Okay. without interfering the converter for other mode. But that is also possible with wind power plant. You may explore it, this also. So here, this is the voltages at generator, but how it is controlled and what kind of wind power model is taken here, that is mentioned here. So some in open DSS for wind power plants, certain kinds of models are there. Model number 1, model 2, model 3. It depends on what kind of technologies you are offering. Some generators are fixed speed generators, some generators are variable speed generator, but these are full speed operation generator. Some generators are partial speed operation generator like DFIG. So depending upon that, there are 2 to 3 models of wind plants in open DSS. So here we have used up model number 1. Then you can notice this is the power generation through wind power plants. It's a negative power. According to convention, if you are injecting the power into the node, it should be negative. If you are absorbing the power through the node, it is positive as per our convention. So that is negative. It's a 1 megawatt according to the mean wind speed, and that you are receiving that much power. Then these are the position of regulator buses. As compared to the previous case, the regulator buses operation. Some regulator buses are in the IEEE 8500 node. So what are the positions of this tapes in the regulators that I mentioned here? Then voltage at the different capacitor buses. Some capacitors are also installed at the different locations to maintain the power factor. So these are the voltage at the capacitor bus. You can notice still at some points your voltage is lagging, even you are injecting the reactive arc through the capacitors. This is for the wind power plant number 2. So basically 2 wind plants are used, okay, and this is for wind power plant, 1 megawatt wind power plant at another bus, and this is 1 megawatt wind power plant at bus number 102670. Now we come with the storage system. Okay, wind power plants are there. Then you are going to introduce the storage. Okay. The storage size we have already shown here. What kind of rating of storage has been used here? Yeah. This with 1 megawatt plants, we have also 1 megawatt hour storage capacity. Now here, this is the power produced by wind power plant 2, because the wind speed model is identical. So here also we are getting the identical power. Little bit you can notice the changes in the node voltages, which is depends on what kind of adjacent loads are there and what is the reactive power demand at that node, that is mentioned. Now with the storage. Okay. So first come with the PV plant number 1. So this is the power injected to the PV plant 1. Because at PV plant 1 there is no storage, so you will not notice any changes in the parameters related with the storage and the terminal voltages. Looks to be identical to the previous case. This is for plant 2, looks to be identical, not much variations are noticed here also. And this is the flow chart of the algorithm used for dispatching the storage systems. Okay. So according to our earlier discussions, we have developed the algorithms, flow charts for this. So use forecast model to determine average wind power generation based on minutes, hourly, daily, weekly, and measure the P wind and SOC of the storage. If P wind is less than average power is less than the instantaneous power, okay, find out the differences If this difference is positive, then you check the storage status, what is the SOC. Because you have to discharge the SOC, and we know that there is a limitation when we can discharge the storage and when we can charge the storage. So if SOC is greater than 20, yes, storage is ready to discharge. So you can provide a command to discharge according to the required discharge rate. That discharge rate also you have to define for each storage. If you have a lithium ion battery, what should be the rate of discharge? If it is a lead acid battery, what should be the rate of discharge? That we have to program. And if this is not the case, then you check whether the wind instantaneous and average both are same. If yes, then storage will remain in ideal case. If this is not the case, then it means the average is greater than the instantaneous. So yes, so now again you have to check whether the storage is not fully charged. If it is not fully charged, then you can switch on to the charging. Not share the activity what you are doing, how it is going to benefit it. That can be obtained if there are some incremental changes, positive changes you noticed in your overall distribution of power. So these are the distribution of active power losses when you are in the base case. Okay, there is no renewable power injection to your distribution network. When you have a renewable power injection but without the energy storage system, okay, so you can notice here the first one which is at the peak is the base case and there is no renewable power injection. So active power losses are higher at every moment of time. Active power losses which are taking place in your distribution network is higher. Okay. When you introduced the DER, so DER is supposed to be orange line. Okay. When you are introducing the DER, the active line losses are going to be decreased as compared to the base case. जब पहले जो losses हो रहे थे आपके, जब आपने renewable energy को introduce किया तो ये losses decrease हुए. It means it is having a want to introduce the DER into the distribution network. And the third case is corresponding to the introduction of the storage system, not at many locations but only at 2 locations, at the wind plants. So we introduced the energy storage system at the 2 locations of the wind plant, and we can notice that there is a incremental decrease in the active line losses in the line at every moment of time. Apart from active line losses, we have a reactive line losses also. Okay. So reactive line losses are also going to be reduced as compared to the base cases when you are having a DER and with the storage. Means overall losses are going to be decreased. Either it is the active line losses or reactive line losses with the DER and storage system. And the third important parameter is your voltage. So what we have done, because it's a large network, you cannot pick up the voltage at each and every point of your network. So what we have done, we have find out the maximum voltage in the network and the minimum voltage. It may be at any bus. Okay. So we obtained the minimum voltage and maximum voltage with the base case. So in base case you can notice the maximum voltage is going to be around 1.085 greater than this, and the minimum voltage is near about 0.9. It is not mentioned here. It is just started the maximum voltage. But in the base case load flow analysis, we have seen that this voltage is around 0.92 or 0.9. So that was the minimum voltage. But if you look at the maximum voltage profile, because in generally when we introduce the DER, the minimum voltage case will rarely occur in the network, but the maximum voltage case will occur. So with the base case, the voltage peaks are greater as compared to the case when we have a DER in storage systems. So with DER in storage, increase in the voltage is little bit, most of the time it is less than the base case. So it proves that the DER and the storage system with the distribution grid helps in stabilizing the network situations, network parameters. One of my PhD students is working in this area. She is Pinky Keshwani. She is doing this kind of research. So he is now exploring another algorithms which are based on artificial intelligence for the same purpose. Presently, if you look at the penetration of this energy, so it is near about 40%. Now we are trying to explore the cases when the penetration of renewable energy with the distribution system will increase further. Okay, then the issues will come. More challenging issue will come. So this is about grid interface. Okay. With this discussion, we are connected with the grid and we have applied the energy storage system. Now we come to the standalone operation. So when we come to the standalone operation, in the very beginning side, we have seen that there are some problems when we are working in the standalone case, right? What are the problems? Because now you have to stabilize your local grid. You have to stabilize the local grid. Sometimes you have a high power generation, less demand, sometimes you have a more demand and high power generation. So operating the standalone plants with renewable energy without energy storage system is practically not possible. Okay. However, in certain situations we can operate, but then we have the limited operating cases where we can operate without energy storage system. So we explored intermittency is one of the problem of renewable energy sources. Then because most of these renewable energy sources are associated with the power converters, so power quality issue will also come in picture. Even you are feeding certain kind of loads which are non-linear loads, then you have to take care about this power quality issues. And another important issue with renewable energy sources is to maximize the power generation, so that you can reduce the size of your generating installation. Okay. If that is not possible, then the size will increase, cost will increase, and you have to bear their retrospective effects. So first come with the wind power technology. These are the technologies which are available, practical technologies. So we have a fixed speed wind energy conversion system. We have a variable speed wind energy conversion system. With fixed speed, we have certain options, like we have a induction generator, spiral cage induction generator, or isolated asynchronous generator, or we have a synchronous generator, or we have a permanent magnet synchronous generator. With variable speed, we have some more options. Okay, not only this option, we can talk about some other options also. Here, these 4 options are there: W-field induction generator, synchronous generator, permanent magnet synchronous generator, isolated asynchronous generator. We may have a permanent magnet brushless DC generator. We may have a switch reluctance generator. We may have a synchronous reluctance generator. All these options will come under the second category, variable speed operation, right? But with the first one, we have only limited cases. Why this is? What is the reason? पहले ऑप्शन के साथ में हमको केवल 3 मशीनें ही अवेलेबल दिख रही है, और दूसरे ऑप्शन के साथ बहुत सारी मशीन्स आ रही है. इसका क्या रीजन है? व्हाट इज द रीजन? द रीजन बिहाइंड दिस इज दैट एट द कस्टमर एंड we were talking about a constant frequency operation, and when we are talking about these cases, then we are not going to use more than one converter or more. But in these cases, we are supposed to use more than one converter. Okay, except if you are going to use matrix converter, because it's a single stage conversion. Otherwise, you have to use more than one converter. So challenges With the standalone cases, voltage and frequency control, harnessing the optimum power, load balancing, neutral current compensation, load leveling, or quality issue. It is not possible with this discussion that we will explore all the cases, so I am just presenting you some limited cases. So this is one case, fixed speed IIG based standalone wind energy conversion. It was my PhD work. Okay, I explored this during the period of 2009 to 11. So here advantages are simple and low cost, cheap and low maintenance. But the limitations are low wind energy conversion, poor power factor, power fluctuation in output, high mechanical stress on turbine components. So this was the work published in Identity Transition and Industrial Electronics in 2010. Okay. So here, this is your induction generator. As I told, only one converter is used. Okay. And then it is connected with the loads. So you have a constant voltage, constant frequency operation in the presence of this 4-leg converter, 4-leg DSC, in support with the battery energy storage system. This is the control algorithm used to guide the operation of this 4-leg converter. 4th leg is used for neutral current compensation because at the load end we don't know whether the load is 3-phase load or single-phase load. So your system should be compatible for this. So this control algorithm for this, these are the results. So basically, this is your generator currents, this is capture currents to compensate the reactive power demand of your IAG. This is the source current, which is the net output to your load, and these are the load currents. In this case, actually, the generation is less than the load demand is more. So battery is supplying the remaining power. These are your DSC currents. This is your compensating current for neutral because load is not balanced perfectly. And this is the power generation through your generator. This is the load demand. So here the power generation is 3.14 kilowatt, but the demand is more, 4.017 kilowatt. So the difference amount of this power is supplied by your storage, which is at the DC link of your 4-leg DSC. Then ultimately we have to take care about the power quality at the load side. So the power quality of your local grid voltage is very good, 1%, and load current TSC is also good, 3.1%, because it's a linear load, not non-linear load. Then these are the results when the speed of wind fall, because in this case we are not claiming the maximum power extraction. So when wind speed fall, generation will also fall drastically. Under this case, battery should take care the responsibility and it should supply. So generation, wind speed is falling, so generation is also falling, so battery is taking care of the deficient power. Another case, DFI is. Now it's a variable speed operation. Standalone case, variable speed operation. What you are claiming in this case? Machine is able to operate at variable speed, so maximum power point taking is possible. Then you are taking care of the voltage and frequency at the load side. So voltage and frequency of the load is controlled, very well balanced. And because now here the DC link is coming between these two converters which are at the rotor side. So battery energy storage is coming here. Okay. Sometimes people have used this energy storage system with the head-on of another converter, which is DC to DC converter. What advantage you will get there? Here I have to use a battery size of around 400 mAh. But managing the battery at little bit high voltage is difficult. So what people will take care do? They will use a buck boost converter at this point. They will take the battery of 24 volt or 48 volt and they will interface with this DC. So this control is usual, or the novelty of this control is that no mechanical sensor is used. Maximum power point tracking was obtained without the help of any mechanical sensor, without the sensing of your wind speed. So these are the results. This is your stator side currents, these are the load currents, these are the rotor side converter currents, and this is the management of your power. So this is the stator power, This is your load power, and this is the power supplied by your rotor side converter. These are the battery currents through rotor side converter, through stator side converter, and this is the TSC of your load source current at the generator side, stator current. This is the TSC of your voltage, okay, and this is the TSC of your load current. This is neutral current. Another combination hybrid case, when you have more than one sources. In the previous two cases, we have either wind, okay, and in this case, along with the wind, you have solar energy also. So this is the hybrid case. It provides the flexibility because both the sources are aiding each other. Wind is available in a greater amount in the night time. Solar is available in the daytime. Okay. So when plenty of wind is not there, solar will take care, and when solar is not there, wind will take care. So combination of these two. So DFIG like previous case is used in this case, and photovoltaic supply system is there. This advantage here you are getting is that you are eliminating one converter. Okay. So PV is interfaced with the help of boost converter with DC link. Then these two converters are naturally required when we have a DFIG operation. Then this algorithm is there. You can refer the paper which was published in IECON in 2016. Another case, hybrid standalone power generation system. This paper was also published in IECON 2016. So here at the you have a PV and you have another case of power generation which is hydropower. So this generator is operating at fixed speed. So it's a fixed speed operation. It will take care about voltage and frequency control, and this converter will take care about voltage and frequency control for this local grid, and DC link is flooded with the PV power also. So whatever the power you are generating from PV is coming to DC link, and then DC link will take care about this converter will take care about how to manage the power generated by this SGIC and this PV, so that your load demand will be fulfilled at the condition of voltage and frequency control, power quality at the load terminal, and the deficient or the surplus power generated by these two sources are to be taken care by this energy storage system, which is present at the DC link through this two back-to-back connected switches. Another case, similar kind of cases where SCIG is there and PMS is there, okay, and then you have two converters, they are feeding to. This is another work in which another concept is coming in picture, where you have an integrated converter. So integrated converter in the presence of battery feeding to your local load. So because you don't know about what is the power generation through this PV, and you don't know about what is the load, okay. So sometimes you have the case when you need the support of solar and battery to feed this load. Sometimes you may have the case when solar is completely missing and you have to feed the load demand through this battery. So there are three different ports in this converter. This is port number 1, which is associated with the solar panel. Port number 2, which is associated with this DC link, main DC link, and port number 3 is associated with the battery energy storage system, and some couple of switches are connected here. It's a very simple algorithm, easy to implement. Okay, this work was recently published in SGSITS 2022. I think yes, 2022. So according to the status of power available, you have the different input ports and output ports. So when these two input ports are available, the output port you have to feed status 1, state 2. When 1 and 3 is available, then you feed power to output port. Output port is your main DC. And then in this case, port 1 is available and you are feeding the power to your load and to the battery. Means power is excess, generation is excess, So we are getting giving this power to load and your energy storage system. In the third case, solar is not there and port 3 is feeding power to port DC. Various modes of operation, according to which power is available to satisfy the load demand. According to that, the switches will come in picture. So these are the different modes. This is a DISO, means double input, single output. Solar is there, battery is there to feed the load demand. Okay. Another case, single input, double output. Okay. Single input, double output. Single input means solar is not there. Okay. You have to feed the power to load through your battery. And the third case is single input and single output. Means battery is there to feed them. So this is the control algorithm. Because PV is there, so first you have to ensure the maximum power point taking through the solar panels. So maximum power point taking is possible through with the help of this converter, boost converter. And depending upon whether this complete power is utilized by the load or excess power is there, then you will feed the remaining power to this basis. So from here you are controlling the duty cycle of S1. S1 is here. According to the sense voltage and sense current, you can feed the power. Lots of algorithms are reported for this. Here incremental conductance method is used. Next case, for the control of all these switches which are with your IDC. Okay. So switch number S2, S3, S4 and S5. These 4 switches are controlled through this algorithm. So you are basically sensing this DC link voltage, you are comparing with the reference value. According to that you generate some reference current, and this reference battery current is compared with the sense battery current, and then a PI controller is used which generate the duty cycles. So the switching up S3 and S5 is together, switching up S2 and S2 is together. Now the switching of this switch depends on, sometime in the external cases you may have the case when battery is fully charged, generation is more, load is not demanding the power, then your system will destabilize. So you have to take care of this also. So basically you will switch this switch only when battery is fully charged, means the charging level is more than the satisfied charging level, and the power generation is more. So you may have 2 options in this case. People are less exploring the interesting option which is going to be coming, which is to manage the control of your solar panel. Right now we are talking about MPPT control. We are not talking about the other point control of your solar panel. The cases are increasing in China, and you have more generation. Okay. They have the wind power generation more than 120 gigawatt nowadays. So they are facing the situations when they have to ask their wind installation to operate at a reduced power, not at the maximum power. So now people start talking about the operation of your wind power plants and solar power plants other than the maximum power. So here you will operate this switch only when the battery is fully charged. So this is for the VSC control, which completely depends on the generation of the local grid to maintain the voltage and frequency and to take care about the non-linear load requirements. These are the loads under the different cases. Okay, single input, double output, double input, single output, or single input, single output. So this is the double input, single output. So in this case, solar is there and battery is also there to feed the load. So these are the switching signals for the different switches and the currents. So this is IL1 and IL3, IL2 and IL3. The important, while we develop such kind of algorithms, and that the important thing is that to minimize the ripples in the battery current as well as the solar PV current. So you will get an optimized efficiency. This is another case, single input, double output, and these are the results under dynamic cases at the variation in the load demand. So how your controller will take care about variation in the load demand or the variation in the generation. Another big concept is coming, which is a smart load, which is taking care of big part in demand response management. Demand response management. In the very beginning I told you that now the time is coming where your load should be also smart. अभी हमारा लोड क्या है? It is not smart. Okay? उसने बोला कि मुझे 100 वाट की पावर चाहिए तो आपको 100 वाट की देना है. Okay? Right? आप it will little bit sacrifice if your grid is not supporting. The voltage will fall, and if it is a static load, then naturally the demand will also rise. But this situation is not good for your grid stability. Okay? So now smart loads are kind of loaded which will adjust their load demand according to the generation. Okay? There are some complications for this smart loads. Okay? So it's like a spring. It's a spring combination. So it's a suspension. When you have the possibility of more generation, you adjust your load to consume more power. When the possibility is that the load is going to shrink, then you shrink your demand also. Okay? So like a mechanical spring, it is basically electrical spring, okay, to stabilize your grid conditions. So this is one of the topology for the different types. In this topology, we have applied a storage system. Okay? This storage will provide you the flexibility that you can guide this source power demand. If suppose you are committing because nowadays the time is coming when your DSO will ask you to reduce your load demand, or it will ask you to increase your load demand because he has plenty of sources. So that time he will reduce the power unit cost. Okay, unit cost will reduce. So you absorb the power when unit cost is less. You reduce your consumption when unit cost is more. So that technology will help for this purpose. So basically it's algorithm. So it is basically ES2, electric spring 2 type of system, where with the smart load is also supposed to be with storage system. So because your theme is just for storage, so I am not showing here the other kind of spring system. So here what we are doing, we are considering this is our driving force. What should be your grid reference? So you decide. Even your load demands for 1 kilowatt, you decide that from grid you will not take care of more than 100 watt. So this reference is coming from this option, and it can be softly computed or softly controlled. And can you guide these 4 switches to satisfy your needs? So these are the results under change in reference grid active power demand. So in the first results, you are changing the load demand according to your pricing mode. Okay. So when you are not comfortable to consume more power, you take your reference to a low value. Okay. So this is the active power demand from your load, from your source. This is the active power demand from your source, and this is the critical load power. Basically here there are 2 kinds of load. One kind of load we are calling the critical load, where you cannot sacrifice. In your house you may have also 2 kinds of load. One kind of load you may sacrifice with the demand. Another kind of load you cannot sacrifice the variation. Take an example of your washing machine. You can program your washing machine to operate at some other period of time. Okay. You may have the kind of your air conditioning system. You may plan to operate at a reduced capacity at some portion of your time. Okay. You may have a electric oven in your house. You may have a geyser in your bathroom. You can guide your geyser and bathroom to operate at a reduced efficiency or capacity. So such kind of loads are there. So the loads can be classified into 2 categories. One is critical load, other one is non-critical. So we are basically trying to control the non-critical loads. We don't want to disturb the critical loads. So whole appliances in your premises are categorized into two categories. One is critical, another is non-critical. So this is the algorithm for this, and these are the results. So under change in grid reference power, you will notice that the grid voltage is maintained at your point, and you are happily feeding your critical load demand without any change. But your spring demand is going to change. Your spring current, non-critical current is also going to change. Okay? Because that is kind of flexible. These are the performance under change in reactive power. Apart from active power, you can also have the guide to change the reactive power. Okay? That is just an option. So here we are not changing the active power demand, we are changing only the reactive power. And your controller, like your state calm, helps you to maintain the voltage in your premises. So these are some parameters which was used in this discussion, and these are the references. Thank you very much. Draw a kind of black box which we are calling converter. Converter is able to supply the reactive power. It can absorb the reactive power, provided we are not supplying the sufficient active power to our converter, or we have designed our converter in such a way that it is oversized. Any other question?
सर जैसे भी पूछे थे कि मैक्सिमम पावर पॉइंट ब्रेकर का यूज करें, तो उसके जगह पर कोई ऐसी डिवाइस अभी आया नहीं है। जैसे आप बोले चाइना में ये प्रॉब्लम हो चुकी है।
हाँ, एल्गोरिथम, आपको एल्गोरिथम डेवलप करना है, डिवाइस को डेवलप नहीं करना है। आपका मैक्सिमम पावर पॉइंट ब्रेकिंग वो हो रहा है वो किसी कन्वर्टर की हेल्प से, जो आपने लगाया है या तो सोलर एनर्जी के बाद में, सोलर पैनल के बाद में लगाया, कभी हम बूस्ट कन्वर्टर लगाते हैं, कभी हम सीधा उसको कन्वर्टर के थ्रू प्लेस कर देते हैं ग्रिड पे, तो हमको उस कन्वर्टर को कंट्रोल करना है। एल्गोरिथम डेवलप कर सकते हो, इट मे बी एन इमर्जिंग एरिया। Most of the algorithms are not there which are compatible to handle such situations. So you can have certain algorithms, okay, which you plan this algorithm, which you develop this algorithm, so that your system should be compatible to handle such situations. As I told you that presently most of this work I presented is for a penetration level of 40% with the grid. But when we explore this penetration level more than 50%, 60%, then such issue will come that your demand is very less but generation is more. So where to go all this generation? Even your storage system will also saturate. Under this condition you have to stabilize your grid. Voltage और frequency तो हमको हर situation में maintain करना है, तो उसको कैसे maintain करेंगे? अगर जनरेशन हमारा बढ़ेगा, एक्टिव पावर जनरेशन बढ़ेगा, I hope you all know that if active power injection to your grid increase, then frequency will increase. So you have to maintain your frequency at 50 Hz.
Okay, thank you sir for your time and discussion. I request my fellow coordinators from our side